And then a shortcut is to actually control click over this one. So if you control click on it, it will give you a temporal viewer. It's like a temporary viewer. Or you can go to here to add to visualization, and choose anything you want, like say a viewer draw or something else. But a quick one to do it is just hold down the control key and click on it, and you will get the result. And those blue things that you're seeing here are the doors. All right, so I'm going to stop here, give you a chance to stretch your legs. I will stay if you would like to catch up or ask questions on the chat window. I will answer that. But let's pause for about 5 minutes, or let's say 8 minutes. We'll come back 10 after 5. And control click is definitely a quick temporal stethoscope. That, yes, definitely. But it will jump from where it was to here. So yes, you're absolutely right. I cannot find scene. Scene is right here under viz, text, and then scene, get objects data. Hi, I got a bit behind. Can you show the tree, please? Yes, absolutely. Also, by the way, Rafael, you can also open the PDF and look at the images if you would like, one by one, like they are in steps. But let me close this a little bit. Oh, shoot. Okay, here we go. Tell me where you would like to see. So basically, get the cluster of faces here, get the building envelope, slice. Let me get this out of the way. So we slice them. We got the faces. We made a cluster out of the faces. We got the door objects as a cluster of cells, and we did an intersection. So this is an intersection. That's what we've done so far. Rafael, is this okay? Is it clear enough for you to see it? Okay, yeah. Thanks, Leon. Sorry, I might have gone a bit fast on these, but as I said, you can catch up a little bit now. See. Right. So let me answer, Ryan. I'm a newbie, of course, but it would seem that if you fed a cell complex into a subtopology node, that you would get a cell complex out of it. Well, the subtopologies would get the subtopologies of the input topology. So if the input is a cell complex, the output, you can select whether you need faces or vertices or edges or wires or cells, etc., or apertures even. So it gives you the one below it, all the way down to a vertex, if that makes sense. Max says, are all adjacency like cell.adjacent cells methods included in the latest version of Topologics? Oh, yes, absolutely. TopologicWorkshop has fully implemented what was in Dynamo and Grasshopper and even more. Like I added new methods that don't exist on Dynamo and Grasshopper. Right now, it's the fastest, most complete. I fixed a lot of the bugs that are in Dynamo and Grasshopper, and added new functionality. So yes, I think that you can look for, let's say, adjacent. So you see topology.adjacent topologies, and you can choose what you want. It works a little bit different than Dynamo, like because I made use of the pull-down menus in Workshop, which are really nice. So you just simply say, okay, what are you looking for? Adjacent what? Adjacent face, adjacent cell, etc. So that's adjacent topologies. Are the cluster nodes in the second Boolean? We got a cluster, right? So let me just check. Oh, wait, let me ask Raphael for 1 second, Ahmed. Are the cluster nodes needed so that the subtopologies are treated as a single element of what its purpose? Yes, a cluster gives you a new type of topology that is a single topology but has many elements in it. Otherwise, replication will happen. Like if I'm feeding 42 faces and intersecting with a cell, I will get 42 other faces, right? Rather than like a cluster of faces. So if you want to combine them into one object and just say it's object A and object B, regardless if it's made out of multiple disjointed parts, you do a cluster by topologies. In the second Boolean, we got a cluster. Let's take a look. So this is the first slicing the Boolean. This is the second Boolean. Yes, we got a cluster, of course, because we got a cluster of these doors. They are disjointed blue doors. So that is a cluster. We're going to get the faces out of that cluster. Yeah, I mean, yeah, it is definitely an optimization. We just found out that instead of, we don't have something like to group. It's going to be basically like a group, how you group objects. So cluster is basically a group, but it allowed us to deal with things that are disjointed as if they are one object, one topology. And it handles the intersections of all the subtopologies within it. Okay, so let me get started again so we don't lose time. It's 11 after the hour. So what we're going to do right now, we are on step 11, if you are following on the PDF, and we're going to take these doors and add them as actual apertures to the cell complex. The cell complex has this idea, or any face actually has this idea of having an aperture. Think of apertures as doors and windows, but apertures don't have to be just faces. They can actually be like a single vertex. As long as you say it's an aperture, it will be recognized as such. So an aperture is an abstract concept. The topology of an aperture could be anything. Could be a cell, could be a vertex, could be a line, could be an edge. Like if you're doing a plan made out of like single line weight, for example, and you want to, put a door as an aperture, you might put a wire or you might put an edge as an aperture. So aperture is an abstract concept. But when we are doing graphs, it becomes important because you can say to the graph, specify to the graph, only go from one room to the other, only if there is an aperture. So now you can, avoid going through floors, through solid walls. All right, so let's go ahead and do that. So we ended up with this cluster of apertures at the very end. So we're going to get the subtopologies out of them. So again, subtopologies. And those are the faces. So we're going to get again the faces. And if I count, let me just check my work a little bit. We have 1, 2, 3, 4, 5, 6, 7, 8 faces. So if I do control click on this, and I get 8 topologic faces here. All right. So those are my apertures. So now it's time to add them to the cell complex. So there's something called topology.addApertures. So topology, and let me get rid of the chat for a second. So where am I here? Oh, I have my caps lock. Topology.addApertures. Right. So the so what I meant, what does this mean? That means I'm going to add my apertures to faces, because you can add apertures to edges, to a vertex even. But I'm going to add them to faces. I'm going to give it those 8 faces as apertures, and the topology is the sliced cell complex, the last one. And I'm specifying that it's exclusive, meaning once you find that this face belongs to another face, stop searching for other faces for it. That's it. That's the one. So one aperture per one face. So you take that face out of the equation. It makes the search a little bit faster. But obviously, if you don't do exclusive, if you have, let's say, 2 doors on a face, then unclick exclusive, and you can add two doors to the same face. Right. So the cell complex, where are they? So the last one is intersect doors and faces to get apertures. No, slice the building, get the faces of the cell complex. So I think it is this one, if I'm not mistaken. Yeah, it is slice the building. So from the slice the building all the way here, let me bring this closer to it. So this is the topology, the building, and then bring it over here and say, these are my 8 faces. I'm going to add them as apertures right here. And if I control click on this one, that's my final, well, my latest cell complex. All right. So these 2, we'll put them in a frame for these 3. Join in a new frame, and I'm going to call that add apertures to cell complex. Great. So step 12, create locator dictionaries. Fantastic. Okay. So find yourself some empty space, but stay in this region a little bit. And let's go ahead and get one of those get data, just the green one by itself. Exit all of these out. Okay, so what we're going to do is get all the objects. So you can select them from here or from here, whatever you want. So this one, let me see if I can do that in the Z. This, I want to make sure I don't miss any of them. And the entrance. We did not call this hallway, but that's fine because we don't need it. And get the selection. And just check that you have everything in here. You can expand it a little bit if you want, just to check your work. Fantastic. So what we're going to do is get the location of these objects and create a topologic vertex out of them. So we have something called vertex by object location. This is, again, obviously specific to Blender. It doesn't exist on Dynamo or Grasshopper. So vertex by object location. And we feed it an object. So we can feed it this object here. And then we have dictionary by custom properties. So dictionary by custom properties. And the source is also the object. Which maybe I should have called it object as well to be consistent rather than source. So that's all can be changed. So let's check what these look like. So control click on it. These are 8 vertices, and these are 8 dictionaries. If you would like to see what these dictionaries look like, you can do something like dictionary.values, just to get all the values of it. And yeah, it's all the dictionaries coming in, but you'll notice there is something called bedroom 1, bathroom 2, bathroom 1. It's all these custom properties, but because I have also, I believe because I have Blender BIM, it probably adds other dictionaries. I'm not absolutely sure, but we're gonna search for them by key. So we're gonna get exactly what we need out of these dictionaries. So locators and dictionaries, and that will be enough for us to set the dictionary. So now we look for something called Topology.set Dictionary. And what this does is that it assigns this dictionary to this vertex. And since we have 8 and 8, it will assign them one to one. This one actually needs an iterate on it. It needs that. I just noticed it doesn't have it, but that's fine. It will do it. So these vertices have these dictionaries embedded in them. So again, the output of this is a new set of 8 vertices. And these vertices, trust me on this one, have a dictionary embedded inside of it. And those dictionaries have all these values. So they are impregnated with these dictionaries. All right. So now, step 13, we need to assign these dictionaries to the cell complex. And because the vertices are in the right locations, they will go to the correct cells. So we are going to get transfer dictionaries by selectors. Transfer dictionaries by selectors. This one. Let me widen it a little bit so that you can see what it looks like. Transfer dictionaries by selectors. So selectors are basically these vertices, which the location of which will determine how they get transferred to what entity or sub-entity they get transferred to. And their dictionaries are the ones that will be copied over to that sub-entity. So if you have a vertex hovering inside the cell, that cell will say, I have a vertex inside of me. So I do a containment test, and it will take the dictionary out of that vertex and assign it to the cell. If you say I'm only interested in faces, then that vertex has to be coplanar with the face. It has to sit inside the face. And then I have a method called isInside, and it will find out that's inside, and it will transfer to it. I do not need all of these to be selected. I think I left them selected, but you really don't need them. You just need to transfer to cells, but that's okay if you leave it. So the selectors are those vertices, those 8 vertices. These are the selectors. And the sink is the last iteration of the cell complex, which is this one, right? We've added the apertures, and now this is our cell complex. So we give it the sink. So sources and sinks, like source and destination. That's what sources and sinks are. So usually there are multiple selectors, but only one sink. That's how I've designed it. And if we take a look at the result, it is a cell complex. Okay. So that's step 13. Now we create a graph. So we get a graph by topology. And so a graph is creating that wire, that kind of like dual graph that is connecting everything to everything. But we are going to choose different options on it. We don't want direct. So direct, like anything that is adjacent that shares a face, it will draw something. So I don't want that. I want to go through the apertures. And I don't want direct if shared apertures, like even though it's Like it says, I can draw you a straight line from one centroid to the other if there is an aperture, but I also don't want that. I actually wanted to go through the door so that it is closer to the idea of a travel distance. Like I wanted to go to the door, from the door to the centroid of the other room, and then maybe to another door. So via shared apertures, through shared apertures. That's what I want. So what is the topology? The topology, again, is the latest cell complex. And I think that is it. So let's actually draw this. Let's find out what it looks like. So this one requires one more step because a graph is a abstract concept. It's not an actual, it's a pure topology. It doesn't have an actual geometry immediately. So you get the topology of the graph.topology. So this becomes a wire or a cluster or whatever it is, because it can take many forms. So let's see what that looks like. This is a cluster because they are disjointed pieces. And then we do topology.geometry. Something like that. And then control-click that in order to see it. And you should see it on the left side. Let me go ahead and give you a 3D view of it. Wait for you to catch up, perhaps, if I went a bit fast. So graph by topology, graph.topology, and topology.geometry. And you see that this is your graph. And you'll notice that it is going right through the apertures. It will put a vertex at the aperture. And you'll notice, for example, that bedroom 1 and bathroom 2 are not connected because there is a solid wall between them. Dining room and bathroom 1 are also not connected because there is a solid wall between them. It's a living room and kitchen the same way. Okay, fantastic. So, right, step 15 is going to be a little bit more involved because we're going to create a Python script and type it in, etc., bring it in. If you want to copy it from the program, whatever it's called, Topologic Test 01, I call it here, but it might be called something different. Let me see, what did I call it here? Yeah, nested list by imported csv.py. I have a file there for you to type it in if you would like. But let's go ahead and quickly create that. So I'm going to go ahead and create, I need to find it now, script somewhere, scripted node light. That's what I'm going to use. So under script, scripted node light. Okay, so we need a scripted node. So what the nice thing about Blender is, oh, by the way, go ahead and save. If you haven't saved, now is a good time to save. Switch over to a text editor. So from here, from this Sverchok thing, just switch over. It doesn't go away. Don't worry. You're not going to lose your work, but just switch it over. Or if you want to use another window, you can do that. So go ahead and switch here, create a new one. And you can copy paste if you want, or whatever have you, type it in. So I'm going to take it from here. And I'll explain it in a second. It's a small Python script. Basically, it opens, I give it a file, a CSV file, it opens it, it reads it. So I have now a big string of all these lists. I split it into rows based on a new line. So anything that is a new line, \n is a new line. So I have now rows. And then I create a table, which is a list. And for every row, I split it by columns. And the columns are separated by commas, because I know they are. And then I create a nested table, and I give the table back out as a CSV data. You shouldn't worry about it. I cannot teach you Python if you don't know Python, but that's basically what it is. So I'm going to call this nested table by CSV file. And I can now switch over back to Sverchok. You see? And here, I can, if you click on this little notebook, you can load it in. And you can click on the plug to load it. And when it's loaded, lo and behold, it has the input and it has the output. So if we switch back just to see where that came from, this was done here. I said the input is called CSV file. It's a string. The default is nothing. It will look at the second level, nesting level. Don't worry about that. And the output is called CSV data. It's a vertex, vertices, but it's also like a string, or actually just data. Or really nested list is just data. Right. So back to Sverchok nodes. We loaded it. It has a CSV file. So we need to point it to the CSV file. So we need a file path of some sort. So let's look for something called file path. Okay, we can click on this and find out where you have saved your Excel CSV, especially if it's different than what I have given you. So let me just check my work a little bit here. This is saved where? TopologicWorkshop 2021-11-19. Yeah, that looks like it's this one. So I will load it, select it, connect it, and then control click to check my work. Oh, why is it a temporal viewer? Shouldn't be a temporal viewer. Should be a temporal stethoscope. Or maybe because I said it's vertex, because it's a V, so it became like it's so thought it was vertices. I don't know if that's correct or not. But anyway, you should get something like this. Okay, where it is neatly arranged, but we're going to now swap those lists. So we're going to do list flip. Oh, where it is? We're going to flip this list, and this is going to be on level 1. And just data manipulation at this point. Oh my gosh, this is also a template. Oh, sorry about that. Just flip on level 1. So you'll see that it flips the list so that I have one list which are, all room A, all the list of all room Bs, and then a list of all the adjacencies. All right. So now we need to get those. So we need to get the first list. So we're going to get list item. Oh, let's get to it here. So we're going to get the first item. So there's something called list item. So we're going to get these. And this is operating on level 1 of the list because these can be nested. And we're going to get index 0. So 0 is the first index, which is the first list. So we get the data from here. And let's check our work. Yep, this is the first one. Just copy paste this. And we're going to get index 1. And again, check your work. This is the second list. If you want to go ahead and get the numbers, you can go ahead and do that. We're going to do them later on. And we are going now to get the vertices from the graph that have these names in them. So as I said before, our graph, this graph, the vertices of that graph have the dictionary. They inherited it automatically behind the scenes from the cells that they represent. And if your aperture had a dictionary, also that vertex would have inherited the aperture. Like it would say, oh, this is a double door, or this is, whatever, this manufacturer, etc. It would inherit all these dictionaries automatically.